Good afternoon, Data Analytics Group. This is a lecture that I will give you on 9/9, September the 9th. So I've written a script, and I think we'll just look through the script a line at a time and see what we get here. So there are some functions you saw in the last R markdown I gave you in a package called psych. I have had this computer turned off since I last used the script, and so I have to reload the library psych. Remember, it's still installed, but it's not active until you make it active with the library command. If you've turned your computer off, or if you started a new project, then you're going to have to reestablish what packages you want to be using. I'm also on this one going to use a different data set. I'm going to use a data set called IRIS, and it's a data set, 150 observations of 5 variables. We'll see what they are in just a second. And I'm using a different data set because I want to be able to do something to illustrate what I'd like for you to do, but I don't want to just give you the code. I want you to figure out the code a little bit. So I'm going to ask you to do some of these same things, but on a different data set. Now we've got the IRIS data set loaded after we say data. IRIS is, by the by, is part of R. It's one of those included data sets, and that's why I only have to give the command data IRIS. And I've ran that before I started this recording. But let's look at names. So we see that the names are sepal length, and that would be measured in centimeters, sepal width, the petal length, the petal width, and then the species. And we can see what these look like with the command head IRIS. And that will give us the first, by default, the first 6 lines of the IRIS data set. If we want more lines or less lines, we can specify. Let's look at the first 10. And we'll say run. And here you can see these are all Setosa. There are 3 different species, Setosa, and I don't remember the others, but we'll get them in just a second. Latin names for the species of IRIS. And the first one has got a sepal length of 5.1 centimeters, a sepal width of 3.5, petal length of 1.4, petal width of 0.2, and so on for the 150. Now let's get some descriptive statistics for this data set. And we're going to get descriptive statistics using the summary command, but I want to get the summary for sepal length and for sepal width and for petal length. And so here's how we're going to do this. We're going to use the tapply function, which is part of the apply family. And you can Google the apply family and you can see what the members are and what their parameters are. But now I'm giving a sepal length. I'm giving a variable here. That would be this first variable, sepal length. And this command then follows with the species, which is over in this last column. And then what do I want is a summary. Now here is what this means. This means to take the IRIS species, and so you're going to look that up. This is a factor in our data set. Let's verify that. Here's IRIS, and we see that we've got length is a number, width is a number, petal length and petal width are numbers, but the species is factor. Versicolor is the second species, by the by. We see here Setosa versicolor, and we still have one missing that we've got to figure out what it is. But the second command here, the second parameter is a factor, And the tapply function takes the place of looping. We could write a loop, a for loop or a while loop, but we really don't have to go to that trouble because of the apply family of functions that we can use. So it's going to set iris species to the first value of species. That would be setosa. And it will do a summary on sepal length, but only selecting the sepal lengths where the species is setosa. And then it will go on to the next species, and then the next species until it runs out of species. Well, there are only 3 here, so it's going to run out after it does 3 species. Let's try that and see what it looks like. Setosa, versicolor, and virginica are the 3 species of irises that are in this data set. Now let's just pay some attention to this since we got the descriptive statistics. We're talking about what variable? We're talking about the iris species length, not species length, sepal length. And I see that for the setosa, it has a mean value of 5.006, 5.93 for the versicolor, and 6.588 for the mean. So these means, they're not all the same. This is 5, this one's about 6. These are fairly close together. This is about 6, this is a little bit over 6.5. So the main question that we're asking today is, are all these means the same? But let's just get acquainted with our data set here. The mean and the median are about the same here, pretty close, pretty close, pretty close. So that tells me there are no real significant outliers. Now we can get just a feel for the variation here by looking at setosa. Goes from 4.3 centimeters to 5.8 centimeters. And that's the range. And the range is not our preferred way of calculating the spread of the data, the variability. But it is one of the measures. And so you can see what the spread is here, 5.8 to 4.3, so that's about a 1.5. And then you could calculate in the same way the range for the other 2 species of data and see if their ranges appear to be comparable or not. Of course, you could do tapply again and get the standard deviations. And so, we might just do that. Why don't we copy this, Control C, paste it in, Control V, and in place of the summary, let's do the standard deviation, SD. And I see that the standard deviations are 3.5, that's 0.35, 0.52, 0.64. So they do have different variability. It looks like the virginica has the most variability, with setosa having the least. Let's get confidence intervals also on the mean. So we want confidence intervals about the mean. And the CI is part of the Gmodel package, which I have loaded. I don't think I've showed you that, but I've loaded it like you load psych, a different package, but CI is a confidence interval function that's inside that package. If I didn't know that, I would Google CI, I would Google confidence interval. In fact, I would Google R space confidence interval, and then I wouldn't get functions from Python for confidence intervals. I would get just R functions for confidence intervals. So that's the best handbook for R that you've got is Google. Keep it by you. Kind of nice. It can't get away from you, can it? So let's look at the confidence intervals anyway. And remember, we're investigating here slowly and in a lot of detail. We're investigating whether these means are all the same. Now I've got a bunch of warning messages here, and that's because the CI has a lot of parameters, and some of them I ignored, and that's giving me warning messages. Warning messages are not errors. Errors mean you've done something wrong, it's not going to work. You get a warning message, though much less serious, and this one says no class or an unknown class. I didn't specify a class here, using the default calculation. So I'm not exactly sure what that means. It was a warning, and I checked, and these values look good, so I didn't worry about it too much. I probably should have worried about it more. But it's telling me that it's using a default calculation, which tells me that for different classes it would use different calculations. Okay, so anyway, we're all right. So what have we got? We've got a confidence interval from 4.9, this is for Setosa, from 4.9 to 5.1 centimeters. And the estimate is just the mean, so it's the arithmetic average. And the standard error is also given here. And that's repeated for the versicolor and for the virginica iris species. And you can see that these confidence intervals, it's a 95% confidence interval. That was the default value that I didn't change, though I could have. The confidence intervals move up. They have a bigger mean, so they're centered around a larger mean as we move from Setosa to versicolor to virginica. Confidence intervals are moving their position, they're moving their scale up. Now, we haven't calculated how wide those confidence intervals are. It certainly would be easy enough. We'd just take the difference of the two endpoints, and that would be worth looking at, but we haven't looked at that yet. Let's look at graphically what these sepal lengths look like by species. And so I'm going to do a box plot, and we're going to box plot sepal length according to the species, and the data comes from our iris function. I'm going to put a title and an X label and a Y label on my box plot. I'm going to fill it with green and color the border around it with black. So let's run that. And here it comes. And I'm going to make it a little bigger for you, so I'm going to go to the zoom and haul that over so you can see it. And I'm going to size it. So here's the box plot of species. I didn't spell, well, I guess what I didn't do was put length in here, box plot of sepal length. So that's an error, by species. And here are my species: virginica, versicolor, setosa. Now remember what the box plot gives me. It gives me the whisker is the lower 25% of the sepal length for setosa. And this whisker is the upper 25%. And the box part is across the interquartile range where the middle 50% lives. And this vertical bar is at the median length for the sepal of the species setosa. And we had been noticing that the mean is getting bigger as the species went from setosa to versicolor to virginica, but we can see it graphically here. The interquartile range doesn't even overlap for the setosa, and for the other two species there is an overlap between the virginica and the versicolor. So I'm just rambling on now and guessing that the difference in the means of these two is probably not due to chance. There's quite a bit of difference here, and most of the data doesn't even overlap here, but there is some overlap here. So in my mind there's some possibility that this difference we see in means would just be due to chance. It's just due to the 150 examples that we picked. So we need to investigate that a little further. And what I want to do is to see if the mean here is equal to the mean here. Simultaneously, I'm going to test whether the mean of the versicolor and the mean of the setosa are the same. And I'd like to test whether the mean of the setosa and the mean of the virginica are the same. So I've got three different pairs of means, three different ways I can pair these means up. And I want to test and see if we've got equality between all of those means, or if some of them are different. Now, I'm going to show you a little bit later in the course that just doing the t-test, mean of virginica versus mean of versicolor, and then the mean of versicolor and setosa, and continuing in that way, doing those three t-tests is not a good idea, and it leads to more type 1 errors. So we're going to use the ANOVA. I guess there's a couple things I put in here that I might as well mention to you that I had kind of forgotten about before we get to ANOVA. One is this coordinate flip. Notice that our graph has the categorical variables on the horizontal axis, and on the vertical axis, I'm sorry. And by default, they would have been across the horizontal axis. And so why did I flip them? Well, these are longer labels, and they don't look all that good spread out horizontally down here. I can use other calls in GG formula and put them on a slant from where they go, but that's more complicated. This seems just easier just to put them over here. And I kind of like the horizontal box plots anyway. So I did coordinate flip, and see I did a plus, so I'm adding that to this command. These commands up here are GF commands. They come from the GG formula package, but the coordinate flip comes from ggplot2. But I had mentioned earlier that usually these play together. The GG formula is really a shell put on top of ggplot2. And so a lot of the things that we need to make them play together are inherited by the GF commands, because they really are just commands that sit on top of ggplot2 commands. And in this case, they play together just real nice, and you can see that I've been able to flip that bar plot just fine. There was another package that I was thinking about using. I decided not to, but I've left the command in here. I had loaded gplots, which is not ggplot. It's a different plotting package. After I experimented with it, I didn't like what it was doing for me, so I left the command in here, but I'm not using any of the commands. The error.bars.by comes out of a package called psych, and it was written to be used in some psychology experiments, but it has some function for us also. And what it's going to do is plot the confidence intervals that we found earlier, and lots of parameters. And of course, you can figure out what the parameters are with a Google search, or you can come down into your console and you can say question mark ERROR, and we're going to be able to get command completion, error bars by, and then we'll press enter, and here's a data file on error bars by. It gives us information on the usage and then all the arguments you can use, and at the end there are details and then some examples. So this is often all the help you need. Sometimes you go to Google also. This seems a little cryptic at first, but it gets better. You get used to reading things like this, but it's so close. It's built into RStudio. It's actually built into, the R language, but just a question mark and then the name of the command, and you get a pretty good packet of information on that command. Well, let's look at these error bars just to see what they look like. I'm not real thrilled with this. I would think I'm going to have to write my own. I want to zoom that for you. I'm going to have to write my own function for displaying error bars, doing that work. I put a label on here, 95% confidence interval for sepal length by species. These are so narrow because the confidence intervals really aren't very wide. There's not a lot of variation in the sepal length, but here's the confidence interval, the 95% confidence interval for Setosa, and it's considerably lower than the 95% confidence interval for the versicolor. And this one has got a wider confidence interval. Now, if they're all 95, this tells me that versicolor has more variability. And this 95% confidence interval is wider yet, and so I know there's more variability here. And I can read somewhat laboriously, I can read the endpoints of the confidence interval off the graph, but that's not really what you make a graph for. You make a graph to give you some quick information, some visual information, and if you wanted the endpoints, well, we've already used tapply and we've plotted these endpoints. We didn't plot them, but we calculated what they are, so we know what they are. It's also possible to print this with the endpoints of the confidence interval printed right out here on the graph. I think it makes the graph a little busy. I would rather have the table and this graph, but you know, different people like different things. Let's see, I'm going to leave that there and just minimize it. All right, so are these means the same? Well, to calculate the equality of 3 or more means, we would use an analysis of variance, and there are multiple packages that'll give us an ANOVA, but the AOV package, which is part of the base R, does a really pretty good job. And so I think we'll just use AOV right now, and we want to look at equality of the means. Now, analysis of variance, it's understood that we're talking about equality of means of sepal length by the species, and our data is iris. Notice that I don't need an iris dollar sepal length because I'm able for this command to give the data as a separate parameter, so data equal iris. And we're going to test all at once if all the pairwise comparisons here have equal means. So let's run this and see what we get. Well, we did get an output, but we assigned it to a variable A3, so there wasn't much showing up down here. But we can now see what the result was by doing a summary of the set created by the AOV command. So we'll do a summary AV, and this is my analysis of variance table, and it gives me the degrees of freedom for the species, 3 species, the degrees of freedom would be 2, and then for the residuals, and the formula for residuals is not just n minus 1 because there are 150 pieces of data. It's the n minus the number of comparisons, and so it's 147. These are the sum of squares, and I suppose at some point in your past you've gone through the analysis of variance mathematically and figured out what all of these numbers are, but we're comparing the in treatment and out treatment variability here, and there's a neat logic to this. We'll test those two estimates of the variance using an F, and the observed F value is 119.3. Well, we could look that up and see if that's a big value or a small value, but this is the p-value over here, and we're going to rely on the p-value, and I see that the p-value is very nearly 0. it's e to the minus 16. That's 2 times 10 to the minus 16. E stands in this case for exponent. 2 times 10 to the minus 16. So that would be 15 zeros and a 2. Now that's much smaller than any conceivable alpha that I would be using, and so I'm going to reject my null hypothesis of equal means. We're rejecting that the three means are equal, but we don't know how they're unequal. Did none equal the other, or is there a pair that are not equal and the others are equal to each other? We just don't know that, and we've got to do a post hoc analysis in order to figure that out. Now, I guess we probably have some pretty good guesses, but we don't have statistical evidence yet. It certainly looks like Setosa and Varsacolor probably don't have equal means by the separation in these confidence intervals, and maybe or maybe not Varsacolor and Virginica, but they very well we could conclude statistically that their means are in fact different. When I look at these confidence intervals, I think that's maybe likely, but we've got to do a post hoc analysis to confirm that. Now there are several different post hoc analyses that one can use, but I'm using one called, it's written by a man named Tukey, and this is the Tukey HSD, which is honest significant difference. The Tukey HSD does a modification on what we would have done if we would try to use 3t-test, but it doesn't use 3t-test. It uses a modification of that procedure in order to take into account the increase in the probability of a type 1 error if one only used 3t-test. Let's apply the Tukey honest significant difference to this ANOVA model, and we'll just run that command. And we get the following. We're doing a multiple comparison of means, 95% family-wise confidence level. That is, the confidence level for the whole procedure is 0.95. So the alpha level would be 0.05. And if I look at the comparison, and this is what Tukey is going to do, it's going to compare species by species for each possible 2x2 comparison. So we're doing Varsacolor versus Setosa. And we see that the p-value is 0. There is, in essence, no chance that the means of these two are the same. We would reject the hypothesis of equality of means because our p-value is less than any conceivable alpha. If we compare Virginica to Setosa, we reach the same conclusion. And Virginica and Varsacolor, we reach the same conclusion. Now, you don't always reach the same conclusion on all of these. This is telling me that none of those means were in fact the same. So that's using a post hoc test, and there are others, and feel free to read up on some of the other post hoc tests. Now we got a few minutes left, and so let's do some predictions here. And again, I think you've probably been over linear and other kinds of predictive models, so this may be review for some of you, maybe not review for others of you. But we're going to use a linear model. Now, that means we're doing linear regression. An LM is part of base R, and it stands for linear model. And I'm going to model the sepal length, and then the tilde, and now a list of my predictors. And the dot here is a shorthand for use all the other variables in the data set to see if you can predict sepal length. So we'll be using the sepal width, the petal length, the petal width, and the species to see if that set of 4 predictors, what kind of a prediction of sepal length it gives me. Data is equal to iris. So we'll run that and get no output because we stored the output in A4, and then we'll do a summary of A4. and we get quite a chunk of output here. Might be better to look at it a little more like this. First piece of output reminds me of what I used to generate this, and I did a linear model where my model, or the formula, was the sepal length predicted by everything. Now the residuals are the errors, and the errors should be normally distributed with a mean of 0. That is, you get a little bit over, your predictions are a little bit too big, some of them, a little bit too small, others, but in the end they balance out. So this information on residuals gives me the median. So this is what in statistics 1 you would have called a 5-number summary. We don't know the mean here, but it gives me the median, and the median is about 0. And I can see that it is pretty symmetric. The third quartile is about as far above 0 as the first quartile is below. Compare these two numbers. And the minimum and the maximum, they're both symmetrically located. So this is probably a pretty good model. My residuals are normally distributed with a mean of 0. That's a really good condition for a model. Now, what is the model that we created? Well, it's a linear model. This is an example of a multiple variable linear model. And I've got an intercept, and its value is here, and I'm not going to read that. The coefficient of sepal width, the coefficient of petal length, petal width. Now, the species was a factor, so it wasn't really a numeric variable. It was a factor with 3 values, and the base value was the one that's missing here, was setosa. So if you're making a prediction and your data comes from the species setosa, you don't have a species factor on the end. If the species you're trying to predict, if the flower you're trying to predict, the sepal length for is of species versicolor, then you would have a negative 0.72356 would be the term on the end for species, which could be combined then with the intercept term. And finally, if your species was virginica, then the end term down here, the species term, would be a negative 1.02350. Okay, so that is what we get when we do the linear model using everything to predict. Now here's more information on the residuals, and here's an important thing. You've learned to look for the adjusted R squared, which is the value that tells me what percentage of the variation in the sepal length is explained by the variables that I've used here to make my prediction, and it's 86%, and I've got 150 trials there, so that's pretty good. That's a pretty strong adjusted R squared. And that's all we need to say there. Now that was my linear model. Let me see if I can find where we were when I pulled this thing up. Yeah, the last thing I want to do, and I know this is running too long, but we came this far. How do we know that we can't get a better model using just some of our observations here, some of the variables, not all of the variables? Well, we can do stepwise regression. There's some controversy over whether stepwise regression is as good as we used to think it is, but it's still taught in most courses. Stepwise regression can go forward or backward. If I go forward, I start with a very minimal model, just an intercept, and then I add the variables in one at a time, and I see if I'm improving the model. Backwards, I start with the model we've just created, the A4 model, and I start removing things from the A4 model to see if I'm improving the model. And I keep taking out as long as I'm improving the model. Now, how do we know if the model's improved? Well, one way of calculating if the model is improved is to look at the adjusted R squared, but there are some problems with doing that, and they have to do with the size of your variables and the units that are being used. Another, and today preferred, method of evaluating a model is to use the Akaike information criteria. Akaike is a Japanese statistician, and his information criteria is actually built from information theory. And think of it, though, for right now, just as an index. And the smaller the index, the better the model. And the index can be negative, so it's still smaller the index, the better the model. So when I do the step here, I'm going to start with the model with all the variables, and we're going to work in the direction backwards. And we're going to keep taking out variables as long as we're improving the Akaike information criteria. So let's run this model, and what did we get? Well, we got that we started with an Akaike information criteria. That is, when we had everything in the model of negative 348.57. In this case, everything that was in that model actually contributes to the goodness of our prediction. And so the step procedure tells us we shouldn't throw out anything. Now here's how it's telling us that. I start with an Akaike information criteria of negative 348.57. The none means if you throw out nothing, your AIC would be negative 348.57. Of course, they're the same. If you throw out the pedal width, see the minus? If you throw out the pedal width, your AIC goes to negative 346.11. Now keep in mind that these are negative values, and so you're getting a smaller value when you move towards 0 here, when you move to the right. That is, when this number becomes smaller in absolute value, it's becoming larger. That sounds crazy, but think about it and you'll see that these numbers are getting closer to 0, which means they're not as negative, which means they're increasing. They're getting better, but small is good for the AIC, and I hope that's what I said before. So I can't do anything to make the AIC smaller than what I had with soup and nuts, that is, with every variable in the model. And so we wouldn't go any further. That's where we'd leave it. Now I didn't know when I picked the model that I was going to play with today that was going to happen. I wish we would have had a model here where we would throw out a couple, but I think you will find that in your next assignment. Now the last thing we're going to do here is just plot our fitted data and our observed data. So let's see what we're doing here. We're doing a point, and we've got a model that we called the step model. Whenever we did the step regression, we got a step model, and so we're going to take out of that model, we're going to take the fitted values, and we're going to use those as our y-axis, and we're going to go to our data set and get the observed values as our x-axis. Now if we did this, if our model was perfect, this would graph a perfect straight line. Because if our model was perfect, we'd always be predicting exactly what the observed value was, and so this would be an x equal y model. I'm going to layer another graph on top of this one. This is going to be a scatter plot. I'm going to layer on top of it. Notice the percent greater percent. And I'm going to use another ggplot function here, GFAB line, and the line will have a slope of 1 and an intercept of 0. You can there are more parameters that you can have, but that's all that we really want. So let's do this. This becomes one command because I've connected them over here. Let's just run this and see what our graph looks like, and we'll make it big again. So this is not real fancy. We could have fancied it up quite a bit and would have if it was for publication, but this point right here is the distance from the vertical axis is the sepal length, and that would be the sepal length that was observed. The distance above the y-axis would be the predicted. Now, if the prediction was perfect, this point would have been down here, right on this AB line that we plotted. So if you look along here, you can see that I've got several points that are right on the AB line. That means for those flowers, that prediction was perfect. And then I've got a bunch that are pretty close, and I've got a few that have fairly big residuals. But all in all, when you're looking at the graph of a scatter plot, that's a pretty tight correlation there. We could have asked R to calculate the correlation. Of course, we didn't do that in this exercise, but you can do that in yours. Now, I'm almost at 42 minutes, and that's embarrassing again because I wanted to keep this down to about 7 or 8 minutes. But we're going to end it right here. This is your lesson for 9-9, and I'll see that it gets posted real soon. Have a good evening.